Welcome. Let's take a look at 1.3. It's called Tracking the Tortoise. It goes back to this race we had before. We're looking at the distance from the starting line for the tortoise and the hare. And what was given is the distance is 2 to the t, distance in meters, t in seconds. So let's look at a few of these. So the first one is, well, what if you are time at 5 seconds or time at 10 seconds? What would be your distance? And for that, you can use that exponential function. 2 to the 5th is equal to 32. So at time 2, you are pretty close here, right? 32. At time 0, you're right at 1. So it almost is on the origin. To the 10th, 2 to the 10th is bigger. I think that's 1024. Wait a second. I need to change this point. So 2 to the 5th, time is 5. It goes up to 32. Should be about there. And then 10 should be up to about 1024, which is about there. So your graph is going to look something like this. Okay. Describe the graph of d of t. So this is d of t. It's an exponential. There's a y-intercept at 0, 1. It's increasing. Okay. Describe the graph d of t. Shelley's distance at time t. What are the important features of d of t? You know, the other thing is going the other way. We would see that for d of t, the domain is actually all the reals from negative infinity to infinity. And these should be like so. And the range, it never quite hits the 0 because it's exponential. So the range will go from 0 to infinity. Okay, so both of those are open also. How long must they wait? For at this point, you know, in the future, you could get some exact values using logarithms. But for now, we can just use the equation, and it works here. 2 to the 10th is equal to 1024. So that would be 10 seconds. Okay, and then you can go ahead and graph that. I started graphing some of the points you can see here. And so my graph is going to be kind of like this, kind of tailing off like here. Okay. What is the relationship between d of t and the graph you've just drawn? Well, here, whoops, sorry about that. Here is d of t. It's your exponential, right? And then when we look at the other one, this is the inverse of d of t. So this would be an inverse graph. How did you use d of t? We just switched the xy values so that we came up with yx, or d and t in this case. Here's another one. Consider the function to the x. What's the domain? Well, the domain here is all reals. The range of 2 to the x, like the last one, is from 0 to infinity. And then the question, is it invertible? Well, if you go ahead, you can see, if you graph these, you can kind of see it looks like that, right? That would be the inverse. And they use f to the negative 1 of x notation. And so in this case, the domain, you can see, is from 0 to infinity. The range is all reals, negative infinity to infinity. And that's a good observation here, is that the function has a domain of negative infinity to infinity. Its inverse has a range from negative infinity to infinity. The function has a range from 0 to infinity, and so in the inverse it has a domain of 0 to infinity. Another thing you might have noticed is the fact that if you graph them with the same scale, and you said f of x equals x, so the two values, x and y, are equal, you can see the symmetry around y equals x. Okay, when you look at those points, you can see each point is the same distance away, and that's kind of a cool thing. So it's a nice little check you can do if you're graphing to see if